So this is Math 2301, Lecture 2. This is August 26th. And so we're discussing today Stewart, section 1.4. All right, let me pull up yesterday's recitation work. So remember that the sequence, if you want to find the web page, for instance, if you want to find the videos of these lectures, you just come to this web page and you show the calendar. And for instance, there's the entry from Monday, including a link to the video from Monday and the handout from Monday. Yesterday's recitation, there's the handout that, if you show the recitation details, we're going to look at that. Now remember how to get here. You just go to Canvas if you want, or you can bookmark this page, but if you don't have this page bookmarked and you've forgotten how to get here, this is a web page that does not live in Canvas or Kansas. It's public. But you can get a link to it by going to Canvas. At the top of the home page for Canvas, there's a link to this public web page. Anybody can come to this page. So let's look at yesterday's recitation problems. We had these problems in yesterday's recitation having to do with section 1.3 definition of limit. Remember, the definition of a limit was that first of all, there's this symbol, LIM, x arrow A, f of x, then equals L. This is spoken. The limit as x approaches A of f of x is L. And what this means now, this is what's called an informal meaning. As x gets closer and closer to A, but not equal to A, the values of f of x, that is the y values, get closer and closer to L, and they may actually equal L. Now, in this definition of limit from section 1.3, I should have said that A and L are real numbers. In a couple of days, we're going to revisit this, and we're going to allow the symbol infinity in some of these places. Now, what this means for the graph, graphical significance, is the graph appears to be heading for the location A comma L. And remember that I don't say heading for the point. I say heading for the location. And the location is given by its x, y coordinates. So x comma y equals a comma L. So on recitation, in this exercise, you had a function given by a graph. So you're looking at how this graph behaves to figure out how to fill out this table. Now, a natural question is there a method for finding limits for a function given by a formula, not by a graph? Well, let me go back to yesterday's recitation some more. You also did this exercise where you substituted in x values, and you just plugged them in and computed the resulting y values, and you observed a trend in the y values, and a trend that sort of sounded like that. As x gets closer and closer to 3, as x gets closer and closer to 3, you found that the y values got closer and closer to 3/5. That's a trend that sounds just like that. As x gets closer and closer to 3, the y values got closer and closer to the number 3/5, so the limit was the number 3/5. So the natural question is there a method for finding a limit for a function given by a formula using analytical tools, not by a graph, not by making a table of values and estimating? So the good news is, yes, there's what's called the precise definition of limit. Remember what I put over there on the board says this is the informal definition of limit. X is getting closer and closer to A. What's that mean? F of x is getting closer and closer to L. Well, what do you mean by that? Can you make that precise? So the good news is, yeah, there is this precise definition, and it's in the book, and there's a beautiful accompanying, world of using that precise definition and computing limits. And I would encourage you to take if you survive calculus, take advanced calculus, where you actually do use that precise definition. That's the good news. There is this precise definition. The bad news is it's really hard. As if this class wasn't hard enough, the precise definition is even harder. So a lot of the stuff that we do in this class will be presented informally, and there's a precise, more difficult, but actually really beautiful world of comparable definitions for all of these things. So that's bad news. We've got this precise definition that would allow us to compute limits analytically, but it's too hard for Math 2301. And most universities at a course like 2301, you don't use that precise definition. Okay, well, so what do we do? Well, the good news, though, is that the precise definition starts to show some patterns. There are some results that always, you can identify cases where the same kind of thing always happens. So in today's class, I've handed out this handout on limits. So what this is results that emerge from using that precise definition. So this amounts to a mathematical theorem, that if somebody else proved that these are the things that always happen. So we can use this theorem in our class. So we're using these limit laws that are the result of using that precise definition of limit, observing these patterns and tabulating them. So that's the topic of section 1.4. I said the topic for today is section 1.4, computing limits. That means we're going to be using these limit laws to actually compute limits analytically. Okay, so my notes. So I want to revisit an earlier example, the example from recitation. So this is example 1. I think I'm going to turn on the spotlights. So the example from recitation, which was f of x equals x squared minus 3x over the quantity x squared minus x minus 6, and this factored as x minus 3 over x plus 1. X minus 3. Wait, that should be x plus 2, right? X plus 2, x minus 3. Okay, so let's compute the limit as x approaches 2 using those limit laws. So limit as x approaches 2 of f of x. Now remember, so using those laws. Now remember, f of 2 exists. If you plug in x equals 2, you get a y value. And then yesterday when you were, I forgot if you estimated the limit. I don't think you estimated the limit at x equals 2, but let's try it. So we're going to compute the limit. Now pay attention to the way that I lay this out on the board. Limit as x approaches 2 of f of x. So that's the limit as x approaches 2 of x squared minus 3x over x squared minus x minus 6. Well, actually, I'm going to do the factored form. Well, actually, no, I'm going to go ahead and do this. Limit is x squared of x squared minus 3x over x squared minus x minus 6. Now, I'm going to put a question mark here. I'm going to say question mark, is this equal to the limit as x squared minus 3x, that is the limit on the top, divided by the limit on the bottom. We're not sure about this step. Why? Well, you're going to see in just a minute. So what would be the limit of the thing on the top? Well, let's see. There's actually a rule if you have a function that's a polynomial, you can just plug in the number. So the direct substitution property says if I have a polynomial, I can compute the limit by just plugging in the number. So what happens? I get 2 squared minus 3 times 2 divided by 2 squared minus 2 minus 6. So that's 4 minus 6, so that's minus 2. The bottom I get 4 minus 2 minus 6. So is that minus 4? So that's 1/2. Is that right? Now I think that's the number that you got. Now, what about this question mark though? Well, the thing is, we wanted to use this rule that says the limit of a quotient is the same as the quotient of the limits. Well, that rule is great. You can just take the limit of the numerator and the limit of the denominator, but that only is allowed if the limit of the denominator is not 0. So when we get to this step and we realize that this is non-zero, that's good. So we can get rid of this question mark and say that this is the result of limit law 5. that the limit of a quotient is the same as the quotient of the limits. Hey, can anybody think of a faster way? Okay, this is a tricky question because I'm the only one who's going to get this. But there is actually a more direct way using the limit laws to get to this answer. And it's here. It's the same direct substitution property again. If you have a polynomial or if you have a rational function and the number a is in the domain, then the limit can be computed by just plugging in the number. So let's just do this problem again. So we have the limit. So another method, another way, is the limit as x approaches 3 of x squared minus 3x over x squared minus x minus 6. So what we have here, this would be x approaches 2. We have a rational function. A rational means a ratio of polynomials. It's a rational function. And the key thing about this is the number 2 is in its domain. Now, how do you know that? What's the domain of a rational function? Or maybe I should say, what are the bad x values? What are the x values that are not in the domain of a rational function?
It makes the denominator 0.
The numbers that make the denominator 0 are the bad ones. Well, you can see from the factored form of this function that the only bad x values are x equals minus 2 and x equals plus 3. So the number x equals 2 is in the domain. So we can just, in one single step, use the direct sub property. The direct substitution property, again, you have to verify that the number a that appears here is in the domain. Then you get to just plug it in. And you get 2 squared minus 3 times 2 over 2 squared minus 2 minus 6. And that equals 1/2. Same answer. So that's the idea of using these limit laws. So again, these limit laws are the result of somebody using the precise definition of limit and very carefully, observing these trends. All right, let's do example B. Using the limit laws. Find the limit as x approaches 3 using the limit laws. Okay, I shouldn't have erased this. Let's try this. Limit as x approaches 3 of x squared minus 3x over x squared minus x, or limit of f of x, sorry. Limit as x approaches 3 of f of x is the limit as x approaches 3 of x squared minus 3x over x squared minus x minus 6. Now, we're starting a new problem here. So we've got a question mark here. Can we do the limit by taking the limit of the numerator and taking the limit of the denominator? Well, let's see how that would look. The limit of the numerator is no problem. I've got a polynomial, so I can just plug in the number. So I get 3 squared minus 3 times 3. And the bottom I get 3 squared minus 3 minus 6. So I get 9 minus 9 over 9 minus 9. So I get 0 over 0. Now, when you're computing a limit, so the number 0 over 0 does not exist. But that does not mean that this limit does not exist. What it means is we don't get to do that step. If taking the limit of the numerator and denominator separately results in the denominator being 0, this means that this is not allowed. So we don't get to use theorem limit law 5. We don't get to say that, if we got to an answer that's 0 over 0, that's undefined. We don't say the limit's undefined because we don't get to go here. So what do we do? We're going to try this another way. We're taking the limit as x approaches 3. Now remember, we know the answer from recitation yesterday. This limit needs to turn out to be 3/5. So how do we get there? Well, first of all, let's switch to the factored version of the function. Now I want you to pay attention to the way I lay this out. X minus 3 over x plus 2 x minus 3. Oh, go back. I'm sorry. I promised Kingsley that I wouldn't. This is Kingsley who's videoing today. I promised Kingsley that I wouldn't keep going back and forth. But I'm going back and forth. This is, if we get to this, yeah, you can just leave there. Well, actually, this will be important. If you get to a limit where you end up with a 0 in the numerator and the 0 in the denominator, you don't get to say that the limit is undefined. What this tells you is you've got to do some other kind of work. So in other words, you can't tell yet what the limit's going to be. And that's what's called indeterminate. That is, you don't have enough information to say what the limit's going to be. So this is what's called a 0 over 0 indeterminate form. Indeterminate because it's too soon to say what this limit's going to be. It might be a number. It might be undefined. We don't know. We can't say. So at this point, I've switched to the factored form. Now, you have to be careful of notation, though, because this equation is saying that this limit is this. That's not true. What I did is I swapped out the function for the factored form of the function, so I still have to have the limit in front. Limit as x approaches 3 of that stuff. So all I did was I swapped out the function. Now, notice again, this is indeterminate. Why? Because if I plug in x equals 3, I get 0 over 0. Hey, notice we can see that this is indeterminate as well. Because if I plug in x equals 3, you can see very clearly I'm going to get 0 over 0. So the indeterminacy is even clearer, and you can see what's causing it. It's that factor right there that's causing it. So this is still indeterminate. Be a great day if I can find my red chalk. But the thing is, remember that this symbol means look at this and consider what's happening to these values when x is getting closer and closer to 3, but not equal to 3. Aha. So I'm guaranteeing that x is not equal to 3. What can you do with this expression if somebody guarantees you that x is not equal to 3?
You can find the value at x equals, that you can find with approaches.
Yeah, but sort of more basic than that. Can cancel. Remember, this is what I was saying on Monday and in recitation is the most important concept of the first month of the course. You can cancel. So I'm going to say this. Since x is approaching 3, this is the idea of a limit, we know that x is not equal to 3. So x minus 3 is not equal to 0, so we can cancel. So I can cancel this, and I get the limit as x approaches 3 of x over x plus 2. And notice that this is no longer indeterminate. I have the limit of a rational function. Basically, the way of thinking of this is if you plug in 3 now, nothing bad happens. So you can do it. But so this is no longer indeterminate. So I can use direct sub. I'm sorry about my handwriting. I've had either too much coffee or not enough. The direct substitution property, remember, says if you have the limit of a rational function and the number a is in the domain, that means if you plug in the number, nothing bad happens, then you can plug in the number. So I can just plug in 3 over 3 plus 2, and that gives me 3/5. Isn't that cool? So that's the same answer that you got in recitation. Now, I want to point out, you'll get tired of me nagging you about notation. But the thing is, the notation is important in this course. Getting the precise notation right and writing things that are correct is key. As I said, maybe in class or recitation, if you end up with a solution where you get the right answer, but you did completely bogus math to get there, it's not valid. So, for instance, here's an example of a bad solution. I'll get my special red chalk. I'm going to put this in red, a bad solution. The limit as x approaches 3 of f of x equals the limit as x approaches 3 of x plus 3, x minus 3, x plus 2, x minus 3 equals 3 times 3 minus 3 over 3 plus 2, 3 minus 3 equals 3 over 3 plus 2 equals 3/5. Perfect answer. This person just canceled here. You got the perfect answer. But it's an invalid solution. As a solution, this is wrong because you cannot cancel zero over zero. Remember, the direct substitution property is only allowed, it says you can only substitute in the number if it does not result in the denominator being 0. So this is invalid. You can't do the limit by plugging in 3 at this point because it results in the denominator being 0. And this is not true. This person made I did this, 2 fatal mistakes. This is not true, and this is not true. I ended up with the right answer, but this is just simply not how limits work. So WebAssign wouldn't care if you did this. WebAssign would say, oh, 3/5, good, check, go on. But this is not a valid solution. So pay attention to this notation. What I want to see is that you can demonstrate how limits work, why they work. That's how the limit works. This is not. All right. So remember again from yesterday, this, excuse me, this function, yeah.
So you're only allowed to cancel it when it's still x minus 3?
Exactly.
You just cancel when you already have the number in?
Right, exactly. This is a limit. It's an indeterminate limit, so I don't know what the answer is going to be. If I really did get to here, the next thing would have to be 0 over 0, which is undefined. So if I really did get to here, the limit would be undefined. But remember I said, if you're computing a limit and you get to a 0 over 0, that doesn't mean that the limit's undefined. It means you can't do it that way. You got to figure out some other way. Yeah, great question. Excuse me, sorry. If any of you watch the video, that's going to be really loud. Sorry, Kingsley.
If we get a problem like that, do we need to write that?
Yeah, I'm going to repeat that question. So the question is, do you need to write this? I really would like you to write this. Yeah, I'm going to want you to explain, because this as I said, is the most important step of the first month of the course. Most people, if you go to the tutoring center and you get a math tutor, they probably are not going to really be able to explain this step. And it's the most important step of the first month of the course. In the second recitation yesterday, somebody used some notation, which was really cool. I'm going to come right back, so I'm just going to turn this up. This is subtle, and I'm always bugging you all to read the book. Read the book, read the book, read the book. The thing is, if you read the book, though, you'll find that the book can be very, very frustrating. The style of written mathematics is that it's so incredibly terse. It's like they think that ink is just this precious thing that you've got to save at all costs. So if you read the book very carefully as an experienced mathematician, you realize, okay, there's something here that looks inconspicuous, but it's actually very important, but you wouldn't know it by what the book says. So that's going to be your part of your struggle in reading the book. Is reading books is always hard. Reading math books is always even harder because they're so terse. So a warning. A warning about the book style. So, for instance, x plus x minus 3 over x plus 2 x minus 3. We discussed this a little bit on Monday. Is this equation true? Well, this is not true. These are not the same function. This is not the same function. The domain of this function is all x that are not equal to negative 2 and x not equal to 3. The domain on the right side is all x that are not equal to negative 2. These two functions are not the same function. The right side of the equation, if I plug in a 3, I get a y value. The left side of the equation, if I plug in a 3, I don't get a y value. So they're not the same. But what I said on Monday, and just again a while ago, if somebody guarantees you that x is not going to be equal to 3, then you can cancel, like over here. Well, if you look in the book, the way they would do this is this. They would just have this thing sort of off on the side. And if you're not paying attention, you might not get what this is about. What this is telling you is you can use this formula, but you've got to restrict the domain. That they don't write all these words. And so if you don't know what this is about, you don't get this, you don't get the significance. You're going to sort of wonder, well, what's that doing there? I'm just going to ignore that. But what this is saying is the domain here, of course, the natural domain is all x not equal to negative 2 or to 3. And over here, the domain is all x not equal to negative 2 or to 3. This has been artificially restricted. So now this equation is true. So this is the book's way of explaining this. But as I said, most students at your level are not going to quite get what are they writing this way for? I don't get this. So I think it's worth, back to your question of do you have to write these words out? I think you should write these words out. Because this is the, if you don't find this confusing, you're not paying attention, because it's confusing. And I guarantee you, whoever you're talking to won't get this unless you write it this explicitly. They probably won't notice it if you do just that. All right. Let's do example 2. So we go until 9:30. Any other questions before I go on? So this is similar to a homework. Find the limit. So the limit is the limit as h approaches 0 of minus 2 plus h cubed minus 8 this should be plus 8 over h. Okay, so now what do you notice about this? Well, what you should always think about noticing is what would happen if I would just go ahead and plug in 0? Well, if I just plugged in h equals 0, I'd get a 0 on the denominator. Okay, that's bad. What about the numerator? Well, I'd get minus 2 plus 0, so I'd have minus 2 cubed. So that's minus 8 plus 8, so I'd get a 0 in the numerator. So this is a 0 over 0 indeterminate form. Now remember, 0 over 0 is undefined, but that doesn't mean the limit is undefined. It means that we can't do the limit by just plugging in h equals 0. Indeterminate means it's too soon to say what this limit's going to be. Now, I think I didn't have enough coffee, so if I were to, I know what this, well, I'm going to write down this answer. And then we're going to see if I got it right. I'm pretty sure that what this turns out to be is the limit as h approaches 0. Now I'm going to copy down all this stuff that doesn't change. But what goes in here? I'm pretty sure this is going to turn out to be minus 2 cubed. This should say minus 2, yeah, okay, plus 3 times minus 2 squared times h plus 3 times minus 2 times h squared, and then plus h cubed. And then there's a plus 8 out here. Again, I wouldn't trust me on this. So let's just see. If I do minus 2 cubed plus, I'm sorry, minus 2 plus h cubed, what do I get? Oh, there's a, no, that's right. Let's see. So this should be, yeah, so that's going to be, yeah, that's right. It's all right. So let's simplify this. So this is going to be minus 8. That's going to be plus 12h minus 6h squared plus h cubed plus 8 over h. And notice that these are all still indeterminate. If I plug in h equals 0, I'm going to get, well, all these things are going to be 0. I'm going to have minus 8 plus 8 on top. That's going to be 0. So this is still indeterminate. But I can do some things here. I can cancel the minus 8 and the plus 8. There's nothing fancy there. That's just arithmetic. So this is the limit as h approaches 0 of 12h minus 6h squared plus h cubed over h. Notice that's still indeterminate. Now, I'm going to keep going. I'm going to want to do some canceling, just as in the previous one we canceled. We can But ahead of that, I want to factor out in the numerator. So this is the limit as h approaches 0. In the numerator, I'm going to factor out a common factor of h. That's going to leave behind a 12 minus 6h plus h squared, all divided by h. The reason I do that is because I want to really hit myself over the head with this and really see what's causing the indeterminacy. That stack of factors is what's causing the indeterminacy. I have h over h. So this is still indeterminate. Okay, so now somebody tell me what I can do here. What can I do?
You can cancel all the h's because h won't equal 0.
Exactly. So this is telling us that h is approaching. So since h is approaching 0, we know that h is not equal to 0, so we can cancel h over h. That's the only thing that I cancel, is that one stack of factors. So I have the limit as h approaches 0, this should say 12 minus 6h plus h squared. Now notice that's no longer indeterminate. Okay, so I can use the direct subproperty. And I get 12 minus 6 times 0 plus 0 squared. All those 0 terms cancel out, and I just get the number 12. So it turns out that this limit is not undefined. It's the number 12. So here, you could just cancel a bunch of h's and get the same result. But I like to go the extra mile, factor out the h so that I can see really clearly it's that stack of factors that's causing the indeterminacy, so that I can cancel h over h. I think I have time for one more example. So notice post-mortem here. This is messy, but there is no nuance here. You just, you do what you have to do. You have to multiply that out. You got to be careful. You can do this on paper by hand. There are no tricks here. Let's do another one. So this is example 3. Find the limit as x approaches minus 7 of 1 over x plus 1 over 7 over x plus 7. So let's do the obvious thing. Let's just plug in x equals minus 7 and see what happens. If I plug in x equals minus 7, I get 0 in the denominator. If I plug in x equals minus 7 up here, I get 0 as well, because I get minus 1/7 plus 1/7. So this is 0 over 0 indeterminate. That doesn't mean that the limit is undefined. It certainly doesn't mean that it's 0. 0 over 0 doesn't equal 0. 0 over 0 doesn't equal 1. 0 over 0 is undefined. But this does not mean our limit is undefined. It means that it's indeterminate. It means that it's too soon to say. Now, I would do something here. Fractions over fractions freak me out. I think they probably freak everybody out. So let's do this. Let's write this. Limit as x approaches minus 7. Let's bring the 1 over x plus 7 out front. and then have a pair of parentheses where I have 1 over x plus 1 over 7. Notice now I have a single baseline. It runs right through the middle here. Here I have two different baselines. I just don't like having fractions over fractions, or fractions with other fractions in the numerator and denominator. So my strong advice is to do that, pull out the denominator and put it in front as 1 over that. And then here we have no choice. We have two fractions that have different denominators, so we got to get a common denominator. There's no choice here. There's no trick. It's just hard. So this is going to be the limit as x approaches minus 7 of 1 over x plus 7. Here I'm going to have 1 over x times 7 over 7 minus 1 over 7 times x over x. I don't know why I thought it was a good idea to try to do this on the sideboard. So again, there's no subtlety here. There's no trick. This is just what we have to do to get a common denominator. So I get the limit as x approaches minus 7. I have the 1 over x plus 7 in front. And then in those parentheses, I should be wearing a Fitbit. I'll be getting in some steps here. I'd get, and this is not minus, this is plus. So this is, I get 7 plus x over x times 7. Everybody follow that? I had a mistake here. I had a minus. That should be a plus. Okay, now notice that all of these are still indeterminate. If I plug in x equals minus 7, I get 0 over 0. But look, having done this algebraic rewriting, you can see very clearly what's causing the indeterminacy. What's causing the indeterminacy is this factor and this factor. X plus 7 divided by x plus 7. So we have the same thing as we've had all class periods. Since x is approaching minus 7, we know that x is not equal to minus 7. So x plus 7 is not equal to 0. So we can cancel x plus 7 over x plus 7. Again, that's a lot to write, but you write that a couple of times and it'll be tattooed on your brain. So this equals limit as x approaches minus 7 over 1 over x times 7. And notice that's no longer indeterminate. That is, if I plug in x equals minus 7, nothing bad happens. So I can use the direct sub property. The direct sub property says if you have a limit of a rational function, this is a rational function, it's a ratio of polynomials, and plug in, and the number negative 7 is in the domain, then you can just plug it in. So I can do 1 over minus 7 times 7. So I get minus 1 over 49. That's the number that's our limit. It's not undefined, it's a number. So again, indeterminate means we can't say yet what the limit's going to turn out to be. We've got to do the limit, we've got to do some stuff. So there are a bunch of problems in this section that involve this kind of thing, doing some algebraic manipulation where you end up identifying a stack of factors that's causing the indeterminacy, and then you cancel, and then you have something you can plug a number into. There are some other limits. I'll get to those. We'll discuss those a little bit on Friday. Some limits involving indeterminate forms where you don't cancel, you use other theorems. There's a theorem called the squeeze theorem, for instance. We'll be discussing that a little bit on Friday. Okay, thanks everybody.